Hey, welcome back. Thanks for joining the channel. Good to see you again. Thanks. Hope you're all well. So today on the bench I have a Kenwood. This is a basic M2A. Now if you remember a few episodes back I had the Kenwood basic M1 on the channel, and this is a bigger sibling of it. This is the M2A. I think it's got more power. It's a lot heavier. It's bigger in size. It's got some nice fluorescent vacuum display power meters in the front here. Level controls, some switches for the metering. It's got speaker switch in the front. But yeah, this is a client unit. He contacted me. He asked if I would look at it. After watching the other video, the M1, he got a hold of me and he wants me to look at this one for him. This one, it has a little bit of a story. He picked it out of a garbage bin behind a pawn shop about 20 years ago, and he's been using it ever since. He loves the amplifier. He wants it fixed, and he wants to continue using this. But he pulled it out of a garbage bin, and it does have some scarring here, really bad scarring. Well, it's not too bad, I guess, but you can see it took a tumble, and it's a heavy unit too. If you pick it up, it's pretty solid. Yeah, so like I said, he got a hold of me. He wants me to repair it for him. He says it has a weak channel. When he's using it, the right is more prominent than the left, or the left fades out. I'm not quite sure on what he meant when he said it's biased to the right. I think the right is more powerful or more prominent. But yeah, look at the dust, even the dust behind the glass here. We can look at this. So I think the first thing I want to do is power this thing up and put it on a load and see what it's going on if we do have a problem with one channel or the other. I had a squint at the schematic for this, and it's very similar to the basic M1, but this one's more robust in that it has higher rail voltages. It's got these special dual transistors. We'll get into that when we open it up and have a look. And yeah, it has an STK module as a driver chip for the power output. So it's a little different in design, but it has the basic bones of the M1. It's just a little more grown up. All right, so let me get this on a load. Let's hook up a scope and let's have a look at what it's doing. Okay, I'm wired in with a 8 ohm load, feeding in a signal, sig generator, the scope connected. Let's do power up first and see what kind of juice this thing's sucking. About 35 watts, relay clicked. Okay. So it's staying pretty stable around 35. It's not going crazy high or crazy low. And our meters, I don't know if the meter's working. Let's turn the volume on the level controls. Let's turn those up first. Yeah, I just want to feed it a signal. I got the speaker shut off. I just want to see our signal. You can see it there. Just going to click this up. And they are both advancing at the same rate. So we're feeding the same signal in both sides, and the meters indicate everything's honky-dory. I don't know if you can see that. Can you see it? So let's turn this down, and I'll put the camera on the scope. Okay, switching on speakers A, and I'm going to start turning up the volume. Looks like everything's normal here. Hang on, I'm going to get a voltmeter on the output so I can tell what kind of power we're pushing out. Alright, so I got a voltmeter connected. Let's try this again. Let's turn up the volume here. Let's take it up to clipping. right there. 44.9 volts RMS. It's doing pretty good. I don't see a level difference between the two channels. Looks pretty identical to me. Now if I manipulate the level controls in the front, controls are clean. I'm pushing 25 volts RMS to the load right now. So what I'm going to do is I'm going to turn this down. I'm going to let it tick away at a lower output. Let's see, probably about 10 or 20 watts. I'm just going to let this thing warm up, and then I'm going to monitor the scope and see if we have one channel drop off or what's going on there. So far I haven't seen anything that's out of the ordinary. So what are we at here? We're at 8.15 volts RMS on the output. So I'm just going to let this cook for a while, and I'll bring you back in a bit. Okay, it's been about 15 minutes now. This thing has been delivering 16 watts a channel into the 8 ohm load for about 15 minutes now, and it hasn't missed a beat, and it's rock solid. I'm trying to bang around here. I don't see anything on the screen that suggests it's a broken connection, cracked solder, dirty relay, anything like that. It all looks good. You can see our traces are aligned pretty much perfectly on top of each other. And I did notice one thing though, that the meter is not registering properly. The right side is lower a little bit than the left. I can show you. Don't know if you can see that with all the reflection and the glare. Turn some lights off. You can see the right is a little bit lower than the left. If I turn the left down, now they're matched. But that's minor. That's a meter adjustment that we can make. We can adjust that. Now I can feel it's getting quite warm on this side. This is where the heatsink is. There's an extruded heatsink. It's only about this long. This is for the entire amplifier. But there is a box fan right in front of it that's pointed this way. It hasn't come on yet. I don't know what temperature range the switch is on. But I thought maybe it would ramp up slowly, but it might just go click and come on full. I don't know. I haven't looked at the schematic for this as far as the fan goes, but it is getting quite warm on this side. This side's staying pretty cool. This is all power supply on this side, and this side it's not even warm. But nothing's going on, so what do we do? Alright, screws are out. Let's have a look inside. We've got a dusty environment. We'll have to take it out, clean it. So here's our little, let me unplug this thing. I'm poking my fingers in here with it plugged in. Here's our thermal cutout switch. It says 80 degrees Celsius on it, so we're not quite there yet. We're over 60, but we're not at 80. Otherwise this fan would have kicked on. And I think this is just a, yeah, this is, hang on, it says 100 volts on that fan. What is this thing? It says AC 120 on the back, but this fan says 100 volts. That's odd. Alright, and this is it. A lot of cobwebs. Yeah, it needs a good dusting. So these are special transistors. These are actually 2 transistors in each package, and the collectors are tied together. So you have emitter, emitter, collector, base, base. I think that's how it goes. These are Sanken DAT 1521P. P is for PMP. And then we have the Sanken DAT there's a difference here. This one is DAT1018P, and then this one's a 1521P. I don't know why they have different transistors there. And then the NPN ones are underneath, and they're both connected to this interface board, which takes all the connections back to the main board where the emitter resistors are located. So it looks like we got tandem outputs on each channel. Now we do have two power transformers under this printed circuit board here. Two power transformers, and then we have our two sets of bulk filtering. This is 10,000 microfarad at 100 volts. Okay, that's the high power. And this one is 10,000 microfarad at 71 volts. So that would be your low or medium power, and this would be your high power. And then we have two caps over here too. I think that what they're doing with this, 5200 microfarad to 56 volts. Not sure what they're doing with this power supply here. Okay, well I'm going to take this outside and blow all the dust out of it before I start working on it. Quite a bit of dust. I don't know if you can see some of the dust in here. If you look down here, you can see the fuzz growing. Cobwebs, dust. Yeah, I'll get that all taken care of. Here's a better look at the transistors. The output devices. I don't see any cracks anywhere though. The main board might have cracks. Depends where the heat's been generated. I'm just removing the felt. The owner put his name and phone number on here, and I don't want that showing up on the video. So I'm just going to remove that quickly. Some alcohol. Okay, pulled the bottom cover off, and I think I know what the problem is. We got cracked solders, and quite a few of them are quite a few places. This cluster of transistors here and this cluster here, these are our drivers, I do believe. I'm not really sure what these transistors are doing, because they have these SDK modules here and here, and I think these modules are the drivers. These might be something else, I don't know, but there's definitely cracks on these. There's a lot of heat on these, and then there's one up here that's cracked. Oh, you can't see. Let me see if I can zoom in and get you a look at what I'm looking at. It's about as close as I can zoom in. This transistor here has definitely got one crack here, one crack in the center. That one's bad. This one here is not too bad. Yeah, but they definitely need to be touched up. All these joints here are kind of scary looking. This one here is especially. This one here is all cracked. And then we have another one. Come on, focus. This one here is cracked. Let's see. You're not getting focus? Go a little bit. Yeah, this one's cracked here, definitely. These three on that transistor. And yeah. So I think that's what's going on here. I think we have probably a combination of two things going on here. We probably have a dirty relay. That's pretty common, and I'd expect it to be dirty. But we also have cracked joints here, and maybe that's what's causing this thing to go weird on them. He never really told me if the fault is there all the time or if it's just at random. But I'm assuming these joints here are not helping. So I'm going to go through this whole board, and like I said, there's some up here too. This transistor here, and probably something else here I'm looking at. There's the wave soldering, factory wave soldering is pretty, I don't know, it's not the greatest. Like it's a good clean solder job and everything, but some of these joints are really low on solder. And that's when you get the cracks developing, is when they don't have enough solder on to give it structure. So I did talk to him about recapping this, and he does want it recapped. So I'll go ahead and recap all the smaller caps. I'm not going to touch these ones. I'll pull them out and test them. And unless there's a problem, they're going to go back in. Same with these two. Well, you can't see them. Same with these two. Although I could probably, well, we'll test them. We'll test the big ones. All the other small ones will get replaced. And then I'll pull the relays and we'll clean those up. And we'll get this thing working again. Don't worry. It's going to be a good project. So we're going to go through and we're going to check some of these caps together just to give you a sense of what kind of shape this thing's in. Let's see, set this up for capacitance. This is a 47 microfarad. Can you read this? I hope you can. Yeah, you should be able to. Okay. So 47 microfarad. 37.9. That's no good. This one's another 47 at 16 volts. 27.5 microfarads. That's no good. 100 microfarad at 10 volts. Oh, this one's down to only 45. So, yeah, I think these caps are completely done. This is a 10 microfarad and we got 8.9. Do a few more. This one's 47. And we're at 37. That's no good. Another 47. We're at 31. That's no good. 100. Another 100. I can get this one in here. 44. Wow, these caps are baked. Another 10 microfarad at 8.7. So I guess my point is these caps here are they don't seem baked. Like the board doesn't look baked. I don't see any evidence of extreme heat, but yet all these caps are dead. And I have a feeling the rest of this is going to be all the same. I did test these two and they're fine. One was up at 5100, one was at 4900 microfarad. So I'm going to leave these two alone. But these here are gone. And then I'm trying to figure out a way to get the main board out of here so I can wash it because it's filthy. I'm just trying to look at the easiest way of dealing with all these wires and connectors. I think I can do it. It shouldn't be too bad. Yeah, I think we can do this. So I'm going to try and get this main board out. That's what my plan is. Okay, I got this thing pretty much ripped all apart now. You had to remove the big can caps to get at the screws for the transistors because the caps were blocking that. So remove the caps. That's okay because you need to clean the board. And once you remove the caps, you got access to these caps because you can't reach them otherwise. So I'm just removing this heatsink. And from everything it looks like paste is quite dried up. It's not much. Well, we're going to redo all this anyways. But these are these special transistors that Kenwood is using. These are dual transistors in a single package. There's two power devices in here. The collectors are tied together, and I think that's the center pin. And then you have two bases, two emitters. So these are wired in tandem for the outputs, and I think they have two different kinds here. They have a DAT 1018P. The P signifies PNP, and then these are all PNPs on top. So we got a DAT 1521P, which is different from this one. I don't know why they used a different transistor. It's a higher rating. And then underneath they have the DAT 1018N. So the N's are your NPNs, the P's are your PNPs, and they're all here on these little bad boards here. So I'm finding a lot of cracked solders on this, so I'm going to this effort of taking everything apart and cleaning everything And but yeah, now I got access to these caps, and there's a cap here that I didn't even see before, and here too, so we'll get those replaced. Yeah, the caps are not great in this thing. They're quite high ESR and low in value, so they're drying up. Another interesting thing Kenwood is doing here, they're piggybacking diodes in each other. I don't know if you can see these piggyback diodes. They got one tacked on top of another one. And these are, what are these? RU4 47s? 47. I don't know what, no, they're RU4Zs. So yeah, these are pretty stout diodes, and they got them piggybacked. So I'm finding these transistors are cracked. This transistor is cracked. Any of these power devices. But the soldering is not great on this boards. They have very light flow soldered, and I think either, well, I'm not an expert on flow soldering, but either it was too hot when it went through the oven, or it went through too fast, or I'm not sure, because if you look at the back, I know you can't see any of this, but some of these barely have any solder on them at all. And if you manipulate the component, then these cracks right away. I can see cracks here already, and I haven't even touched those things. So I'm going to reflow a lot of this board. There's a lot of problems with the soldering on this, and yeah. See, these ones are cracked here, here, here. That's that cluster of transistors on a heatsink. So I'll get to this. I'll deal with all the back after I get the caps, new caps in. Just going to quickly go through these. There's two relays here. I think they're using one relay for each channel, or sorry, set of speakers. And let's check the contact resistance on these quick. I have a feeling these relays were problematic. So this one here, well, this is not good at all. It's 12 ohms, 3 ohms, 25 ohms. That one's really problematic. Okay, let's try the other, quickly go through these. Here's the other side, 2 ohms, not good. Here's the other relay. Well, we got about 700 or 800 milliohms, 1.5 ohms. Yeah, not very good. So these, here's the last set of contacts on the second relay. 10 ohms, 9, okay. These will get cleaned, and then I'll show you what they look like after. Alright, here's a quick look at the after, and all 4 sets of contacts are about the same. Turn this thing on. 12 milliohms, 12 milliohms, and it's repeatable and accurate. So I'll get these popped back in. So I really question Kenwood's design philosophy with this amplifier. Now don't get me wrong, I'm not Kenwood bashing right now. I'm just trying to figure out why they went this route, because I wouldn't choose having these special transistors mounted on these little independent boards with these skinny little wires running back to the main board. You got to remember, this is a, you know, what did I measure? 44 volts on the output, so that's like 250 watts per channel, and they're doing this. You got current running through these wires. This is a high power amplifier, and they're using these little piddly wires to run. There's a lot of current flowing through these output devices, and you want to have as low impedance as possible, and you want to have high current path for because these big caps are going to supply current to these devices, and then you got these little wires. So that's what I'm questioning here. Why did they choose to do it that way? Another thing is, they use these dual package transistors. There's 2 transistors in each one. I'm sure if you do the calculations, you're going to be okay, because the amount of surface area on the backs of these transistors determines its power dissipation rating. You can only get so much heat through a certain how many square centimeters of area. If you want to get more heat, you have to increase its surface area. But these transistors, you got 2 transistors in each package, and they're sharing the heat spreader and their thermal connection to the heat sink. I just don't see an advantage to that either. So yeah, I kind of question, why did they even make these transistors to begin with? Are they trying to save space? Do they really need to try and save space in an amplifier this big? It's a big case. It's got lots of room. There's lots of empty space. They chose, instead of increasing heatsink size, they chose to put a fan in, which is another design curiosity I have with this Kenwood amp. Like I said, I'm not trying to bash this. I'm just trying to question, why do they do all these things? This is going to be a great sounding amp when I put it all back together and start listening to it again. I just don't understand their choices. But here we are. So I'm putting things back together. I need to paste these back on. Fresh compound. The compound was pretty much dried up. It was about a 50-50 dried up. It was still holding out, but not the greatest. And then I want to resolder some of these little daughter boards here and make sure we have good connection on all those. And then recapping's done. I don't think I'll do anything with the potentiometers. They sounded fine when I tested them, so I'll leave those alone. These switches are for the meter. Yeah, so I'm just in the mode of putting things back together, and I wanted to turn on the camera a bit and talk about that. The relays, they tested fine. They're about, on each contact I have 12 milliohms now, down from before. Alright, so I'll get busy here, and I'll bring you back in when it's time to fire this thing up. Alright, so I think I'm ready to do the first power up. Let's try this out. Can we see this? Alright, here we go. Went up to 85 some watts. Clicked on. And we did get a meter on this side. Let me try that again. Maybe we get both meters working. Just a little bit of noise on the right channel. Okay. Everything looks normal. I'm going to let this power up for a while, and I'm going to adjust bias current. There is bias adjustments here. There's one here. You can see this. It's hidden by the wires probably. And then there's one over here. And we can measure right across these emitter resistors. The tops of them have the little wires sticking out the top. So we can just connect our voltmeter there, and we can test for voltage drop across each emitter resistor. And then I can set it accordingly. I don't know what the value is. You have to go look it up. All I have right now is a schematic. So this is what we're drawing, which is fairly typical of an amp this size. I'm going to go see if I can hunt down a value for the bias setting, and then I'll let this power on and warm up, and we'll set it to the correct value. Alright, it's been on for about 15-20 minutes. Bias is up now around 14. Now I was reading online just now, and I guess bias should be around 13 millivolt mark, and here's our power consumption. So, and this is starting to warm up a bit. So it's not far off from our target. On this channel anyway. I haven't checked the other channel. Let's check it right now while we're here. If I can see, what do we have? And we are bang on our mark on that channel. I don't know if it's left or right, but so leave that channel alone. I'm going to adjust this one down just to match, and then we're going to be good to start doing our power test. Okay, so for the adjustment of the power meters, you got to take your front panel off, and then you have your adjustments right here. These two are your level, left and right. It's all marked, and these two potentiometers here are for brightness. So if I take this and turn it, it's already maxed out. But I can turn the brightness down on one or both of them. These are both maxed out. And if you are a purist, you might want to turn these down, because the brighter and harder you drive a vacuum fluorescent display, the shorter life it's going to have. So if you want to turn these down and increase the life of those tubes, you can do that. But they're both okay. I think they're fine. So what I'm doing here is I'm feeding a voltage in on the signal generator, and I'm measuring the output. And when I have 20.5 volts RMS on the output, that's my 20 watts. So what I did is I adjusted this left channel, so just the 20 watt bars started lighting up. And now I need to do the right channel. So let me see here. I just got to turn this one up a bit because I'm not there yet. And oh, there we are. I went too far. So right there, I think, is 20 watt level. And then you can turn the signal generator up and down. And if they track together, which they are for the most part, looks like the right is a little more aggressive than the left. So I'm going to turn the right down. And turn the right down until we have equal. It's a very fiddly adjustment. Right there, I think. Let me try that again. That's better, I think. Both tracking together. Well, not entirely. I'm going to keep playing with this until I get it right. They're both in sync with each other, and they're both accurate to the voltage we're putting out. Okay, here we go. Got it all connected in for a power test here. I got my load. Now I'm going to say right now, I don't know if I'm going to do full 10 minutes at full power, because we're getting, what, 250 watts a channel. And I'm going to have a fan going on my load here. But I think I just want to get this hot enough to confirm if the cooling system here is working properly. This 80 degrees Celsius switch, when it hits 80 degrees, this fan should come on, start to cool, and if the temperature drops enough, it should shut off again. We'll see. I don't know yet. We're going to see how well this goes. This arrangement of all these clusters of transistors packed in here so tight, this isn't ideal. You'd like to have a bigger heat sink with this spread out more in a traditional layout. But I think they're relying heavily on this fan to do all the cooling at high power. Now, this thing rarely sees, I don't know if this thing ever had the fan turn on. Judging from the layers of dust that were on the fan when I cleaned it, it looks like it hasn't moved in decades. So I don't think the fan is ever kicking on. I don't think it ever gets hot enough. So let's go for it now. Let's turn this thing on. And she up in the scope. Relay click, and we do have our signal connected. No, we don't. Give me a second here. Alright, signal's connected. Let me turn this back up. And there's both our channels. I'm going to adjust volume with the signal generator here. So I'm going to adjust that. Let me adjust my probes for 10. Let's turn this up. I have my voltmeter going. Alright, I think we're good. What I need to do is turn that down, turn this up. Here we go. There's clipping. Back it off. Alright. So I'm at 44.6 volts RMS. And let's start the timer. I'm going to put this right up here. And this is what we're taking in. 760 watts. We've got some watts coming out. I'm going to turn on my fan to cool my heatsink here, and then I'll be back in 10 minutes or less. Well, we're 4 minutes in. Our heat sink. Not even. There's 85 over on this side. 70 some on that side. So expect it to go on any minute now. There it goes. 5 minutes in, the fan comes on. That should remove a lot of heat. Fan goes off at 5 minutes 30 seconds. So it does cool it down. I expect it'll cycle back on again. There it goes again at the 6 minute mark. Alright, we're at the 10 minute mark here. Let's shut this down. Turn down the output. And shut this. So, it's working as designed. It's working well actually, this cooling system. I just wanted to make sure it was functioning, and it's cycling on and off. It's keeping the heatsink down around the 80-degree mark. And this worked pretty good. I was pleased with it. So let's set up and do some square waves. I'm going to let everything cool down here for about 5 minutes with the fans, and then I'm going to come back. We'll do some square waves. Okay, I think that's good enough. I'll shut this off. I'm running about 6 watts per channel output from square waves, and this is what we got. Looks pretty good. 1000 hertz tone. Let's go down in frequency. Actually, first let's test these controls. So this is the left and the right. They're both pretty clean. As you can see, there's no scratchiness, so this shouldn't present a problem in the future, or the near future. So that's good. Okay, let's go down in frequency. Let's see here. Let's go down to 100 hertz. And 100 hertz looks exactly the same as 1000 hertz. This thing's incredible. Look at this. Okay, let's go down farther. 90, 80, 70, 60, 50, 40, 30. Yeah, this is a nice amplifier. Look at this thing. 30 hertz, 20, 10. Barely any tilt at 10 hertz. That's what you want from a nice big beefy amplifier, is just do what it's told and not do anything weird. Alright, let's go to the high end. Okay, we're back at 1000 hertz. Let's go up in frequency. $10 kilohertz. This is a fast amplifier too. There's 30 kilohertz. Start to see some rise times. Okay, 30 kilohertz. Let's go up. lose it right around here somewhere. This is 80 kilohertz. Doing really well. Very nice amplifier. I like it. Alright, I separated the caps that I took out of this amplifier into two piles. I don't know if you want to make a guess right now which pile is which. Put your comment down below. I don't know if you want to play that game, but I'll tell you right now, these caps are okay. These ones have all failed. Yeah, I'm talking failure. Like, what do we got here? For example, here's a 470 at 16 volts. Let's test it and see. Just quick, like, I'm going to take up your time with this. I could go through all these caps and show you how badly they degraded, but right now we'll just do one. And for now, this one here measures 270 microfarad. It's got a 300 milliohm ESR, which is, this cap's done. It's failed. It's down to half its value. So that's pretty typical of all these. They're all down in value, high in ESR, more than the 20%. So they're all gone. These ones were okay. They're still holding out, but they show weaknesses. Like, they still have high ESR on some of them, and I don't think they're too far behind these other ones. So that's all we put into this for parts, and nothing else was changed. And yeah, that's it. Well, there you have it. That's as far as I'm taking this one today, and I'm going to test drive this for a while. Probably give it a week or so on the bench of listening before I return it back to the client. And I think I have a feeling I know what this is going to sound. Well, I don't know yet, so shouldn't comment on that, but I have no doubts it's going to be a nice sounding amplifier. It's got some good power behind it. It's got some nice features. I like the vacuum fluorescent display. That's cool. And the adjustable inputs. It's a nice amp. Doesn't have the Sigma drive. That's what I kind of thought was weird, is this thing doesn't have the Sigma drive, the basic M2A. I think the basic M2 does have the Sigma drive, but the A, they eliminated the Sigma drive on the back. Don't know why they would do that. It's an interesting choice on design, but alright, so I'm going to end it here. Thanks for watching. Take care, and we'll see you on the next one.